Hello, welcome to S Chemistry. Myself Dr. Suhas Gauri, and today I will be teaching BSc 5th semester Physical Chemistry course on colligative properties of dilute solution. So here is the outline. So first I will introduce the term colligative property, what is meant by colligative property that we are going to see. Secondly, relative lowering of vapor pressure of solvent in a solution, followed by elevation of boiling point of solvent in solution. So let's start with the colligative property. So the term colligative, as the word suggests, so the colligative, that word came from Greek root word which is colligates, that indicates the meaning of collected together or depending on the collection. So here we are collecting uh, the property of the complete solution. So this colligative property is only for the dilute solution. So colligative properties are the properties of only dilute solution which are suspended, supposed to behave as a ideal solutions. So your solution, that ideal solution, dilute solution should be follow as a behave as a ideal solution. So dilute solution, you can consider example of uh, 1 gram of sodium chloride dissolved in 1 liter of water. So we can consider as it's a dilute solution. So what are the properties of that dilute solution? We call its colligative properties. So that is the solution in which the activity of the solute is equal to its mole fraction. So mole fraction is basically completely depend on the solute. If your solute is non-volatile, so that indicates your whole, whatever the you have added the solute in the solution, it will remain and it will be always equal to the mole fraction. So here the criteria is your solute has to be non-volatile. So we will see the definition. So a colligative property is a physical property that depends on the relative number of solid particles present but not their chemical identity. So this property only depends on the solute of the particles. So how many number of solid particles are present in the solution, the properties only depends on the colligative property. So but not their chemical identity. So we don't consider the which are those solid particle made up of that which chemicals, so we don't consider in this case. So these properties in fact depend upon the nature of the solvent. The colligative properties can thus be rightly regarded as the property of the solvent in a given solution. So properties of the solvent is in a given solution. So properties is um, so major in dilute solution, major component is solvent. So we can consider as the property of whatever the colligative property is coming, that physical property which is only majorly responsible for the properties of the solvent in a given solution. Now we will see the second point, that is relative lowering of vapor pressure of solvent in solution. So what is meant by vapor pressure, that we are going to see. So what is the known fact about the solution of dilute solution? So you can consider a two part like beaker. One beaker is full of pure solvent, like half of pure solvent, and another beaker contains solution, which in that solution you have non-volatile solute and volatile solvent. So these two types of beaker is there. So here you can consider, if pure solvent is there, so it has some vapor. If you cover this beaker with the help of lid, you will be having some solvent particle which is in the vapor phase. So whatever the vapor is there, for that vapor pressure we call it vapor pressure. uh, Now consider in second beaker, now you added non-volatile solute. Okay, so non-volatile means that can be sodium chloride, for example sodium chloride or potassium chloride, or you can consider as a sugar or lemon. So in that case your solute will not go in vapor phase. So what will happen, so that solute will absorb the solvent molecule. So since this is the dilute solution, so less number of solvent particle will be in the vapor phase. So that's why you will be having vapor pressure, it will be less than the this pure solvent vapor pressure. So we call it lowering of vapor pressure. So this is the fact. Now we will see, so here you can denote this vapor pressure by pure solvent we denote by PS naught, that is vapor pressure of pure solvent, and PS equal to, and for the solution vapor pressure we denote it as a PS. So that is the vapor pressure of the solution. So now when non-volatile solute is dissolved in a liquid, the vapor pressure of the solution PS becomes lower than the vapor pressure of the pure solvent, that is PS naught. When non-volatile solute is dissolved in a liquid, the vapor pressure of the PS becomes lower than the vapor pressure of the pure solvent, that is PS naught. So this is the photo of Francois Marie Ralts. So this is the name of scientist, that is Ralt. So in 1899, Ralts succeeded in establishing a relationship between lowering of vapor pressure of a solution and the mole fraction of the non-volatile solute. So lowering of vapor pressure of a solution and the mole fraction of the non-volatile solid. So let us consider a solution obtained by dissolving n mole of non-volatile solute in capital N mole of volatile solvent. So this is the one kind of solution where your solute is non-volatile and solvent is volatile. So how you will calculate the mole fraction of solvent? So here is the formula. So mole fraction of solvent, that is denoted by x1 equal to capital N by divided by n plus capital N. So here mole fraction of solute, that is x2 equal to n by n plus capital N. So this is a mole fraction of solute. So the vapor pressure of the solution is merely the vapor pressure of the solvent. Vapor pressure of the solution is merely the vapor pressure of the solvent, because your solute is non-volatile. So whatever the solvent vapor pressure is there, that will be same as the solution. That is the approximate. So according to Raoult's law, the vapor pressure of solvent, that is PS, is an ideal solution, is given by the expression. So for solvent you can consider, if you are so this vapor pressure is only for the solution, and for that you know, if you know the vapor pressure of the pure solvent, if you multiply with the uh, mole fraction of the solvent, then you can get the vapor pressure of solvent for that ideal solution. So where PS naught is the vapor pressure of the pure solvent. Since x1 plus x2 equal to 1, because if you add 2 mole fraction of like solute and solvent, it has to come as a 1. So equation, if you put this equation 1 into this equation, x1 plus x2 equal to 1, you can rewrite that equation in this way. So PS equal to 1 minus x2 bracket close into PS naught. So that is equation number 2. So x2 equal to Ps naught minus Ps divided by Ps naught 3. So equation 3 is usually called relative lowering of vapor pressure. Relative lowering of vapor pressure of solvent in solution. So Ps naught minus Ps divided by Ps naught equal to n by n plus n. So this is we will consider as the equation number 4, where small n is equal to number of moles or molecules of the solute, and capital N represent the number of moles of or molecules of the solvent. So the lowering of vapor pressure of a solvent depends upon the number of moles of the solute and not upon the nature of the solid dissolved in a given amount of the solvent. So whatever the vapor pressure will be lowering due to solute, so that is only depends on the number of moles of the solute and not on the nature of the solid dissolved in a given amount of the solvent. So because here your solute is not reacting with the solvent. So hence lowering of vapor pressure is a colligative property. So that's why since the it is 100% depends on the nature number of moles of the solute, so that's why we can consider as a lowering vapor pressure is a colligative property. So moving to the next point, that is elevation of boiling point of solvent in a solution. So let's start. So what is meant by boiling point, that we are going to see first. The boiling point of a liquid is the temperature at which its vapor pressure becomes equal to 760 mmHg. Since the vapor pressure of a solution is always lower than that of the pure solvent, Ps is less than Ps naught. So the boiling point of a solution will always be higher than that of pure solvent. The elevation of boiling point is the difference in boiling point, that is delta T, between the solvent's Tb and solution's T boiling point. Just for the sake of definition, the elevation of boiling point is the difference between of boiling point between the solvents and the solution's boiling point. So consider you have water, and if you add 10 gram of sodium chloride into the 1 kg of water, and if you boil that solution, you will get the boiling point, that is T. So the difference between these two boiling point will be considered as a elevation of boiling point, because vapor pressure of solution is always lower than that of the pure solvent. So due to difference in vapor pressure, you will be having different boiling point of the solution. So whatever, if you add any solid non-volatile solid molecule, boiling point of the solution will be always higher than the pure solvent. So here Tb represent the solvent boiling point and T is represents the solution boiling point. So if you minus T minus Tb, you will get the delta T. So delta T is nothing but your elevation of boiling point. Let's consider using this the graphical mode. So you have on y-axis you have vapor pressure and x-axis you have temperature. Suppose you have any solvent, consider as a water. If you start boiling, if you start heating that solvent, so your temperature will continuously will increase as you go towards the right hand side of this temperature. As temperature increasing, your vapor pressure also will increase. So at one point you will be having boiling point of that particular solvent at particular temperature. So that will be the boiling point of the your pure solvent. So here it represented by capital A. So this point represents the boiling point of that solvent. So at that point you will be having pressure, that will be having 1 atmospheric pressure. So now consider you, if you added sodium chloride, if you added like 5 gram of sodium chloride, if you added in that solvent, you will be having solution number 1. So solution 1 will be having different boiling point. So since we have seen, if you add salt or non-volatile solute, you will be having lowering of vapor pressure. So because of that, you have to heat little bit higher, you require more temperature. So that's why the solution 1 graph start from the slightly later than the pure solvent. So as the temperature increasing, so your solution will start getting boiling. So this graph A, line A, and this line B, so this is almost parallel to the first line. So as the temperature is increasing, your boiling point will at after some time it will reach to the boiling point. So that boiling point will never be same as the solvent boiling point. So it will come as a capital B. So here T1 is represent the boiling point of B. And if you further add more solute to the same solution, you will be having further boiling point will be further shifted towards the right hand side. So as this graph shows, your solution to temperature shows here. So as the temperature increasing, your boiling point also solution 2 will be increasing. So at certain time you will be having C. So this is your C. So the vapor pressure curve of the pure solvent of the solution 1 and 2 with different concentration of solute are shown in figure. So for this figure we call it Ostwald-Walker method for measuring the relative lowering of vapor pressure. For dilute solution, the curve BD, so the curve BD and CE are parallel of straight line approximately. So for here you can get the triangle, for similar triangle A A C E, and this triangle is it similar with triangle A B D. So we have AB divided by AC, and next we will be having AD divided by AE. So this line is parallel with the corresponding with the AB is corresponding with the AC. So it's due to similar of this triangle. So from this you can get, so T1 minus TB divided by T2 minus TB, and for AD you can represent as a P minus P1, because this distance is equivalent to the P minus P1, and this AE distance is P minus P2. So from here graph you can get this equation. So if you further so you know that the pressure here P minus P1 and P minus P2 are the lowering of vapor pressure of the solution 1 and solution 2 respectively. So these are the pressure of the lowering pressure of the solution 1, and this is for the lowering pressure of 2. So hence the elevation of boiling point is directly proportional to the lowering of vapor pressure, that is delta T is directly proportional to the P minus Ps. So here Ps means the solution pressure, vapor pressure of solution. So if you minus it, so it will be always the directly proportional to the elevation of boiling point. So since the vapor pressure is directly proportional to the number of mole of the solute, so you can directly say as the elevation of boiling point is a colligative property. So this property elevation of boiling point, so this property is also depends on the how much number of mole you are going to add into the solution, that is solid molecule you are going to add to the solvent. So that is always depends on the number of mole of solid. So that's why elevation of boiling point is a colligative property. So here we came to end of this lecture. So these are the references for further reading and references for books as well as image. So thank you for your kind listening. See you in next lecture. Till then, happy learning.